mention two quick notes before I jump into my introduction to Earthspots. First, the coupling mechanism, the induction mechanism that we just saw Bruce present to us as the form of energy integration that we don't know enough about. That's the same type of ground, atmosphere, ionospheric induction that I was talking about earlier. So I think Bruce and I need to have a chat here at some point pretty soon. The other thing I want to mention real quick is I have to correct a fact that I stated earlier. The breadth of the study on the solar polar fields was over 35 years and over 16,000 days. I sort of mashed them together when I was up here and a little nervous under all these lights, and I said 35,000 days. Somebody caught it, and I want to thank you, but it was over 35 years, 16,000 days. Anyway, we're here to talk about Earthspots, and what Earthspots are, if I can push the right button, they are the Earth's version of sunspots. Now, the comparison of sunspots to Earthspots goes back decades, but with some of the new tools we have, we are able to learn a bit more about them. Now, for the first part of this speech, we're just going to be looking at these sunspots while I sort of explain to you some of the similarities between sunspots and Earthspots. And then we're going to actually go live on the internet and take a look at where the current Earthspots are and how they're interacting with us. The reason why we are just having this one frame, me talking in front of it, and then the live demonstration is because had a little bit of a short window to prepare for this. I'm actually filling in here, but I'm happy to do it. This is one of my favorite topics that there is. So, let's just start with a sunspot. When you look at a sunspot, you see a dark, often black core that we call the umbra. And then, it's tough to see on some of these images, but around it, there is an orangish area called the penumbra that you can see. Umbra in the middle, penumbra on the outside. And if you could zoom in, you would see that this penumbra is not just a blotch of orange. These are actually electric currents, and they form these lines within the orange that all point back towards the center of the umbra. So imagine you have this dark sunspot core, and that orange thing all around it, they're actually lines all pointing in towards the center. If you were to come up, bear in mind, this is basically the surface, the photosphere, what we can see down to the sun if we block out the glare. But if we come up into the corona and we use the Solar Dynamics Observatory and some of the other satellites, we often see swirling clouds of plasma and charged particles above this. Now, because there are so many spots on here, the swirls take all different kinds of shapes. But every once in a while, you get a sunspot that is a loner. We call these an alpha spot. They're just all by themselves. They don't have positive and negative spots. It's just the one. And when you can isolate an alpha spot on the sun and you look up into the corona, the sun's atmosphere, you're going to see the swirling curves of a hurricane, all bending the same way away from the center. So you come and you take a look at a satellite image of a hurricane on Earth. And you guys can do this, just pop on Google and type in hurricane. You're going to see the eye, just like the umbra on the sunspot. You're going to see the swirling clouds that we've all come to know in a hurricane, just like you would see in the corona on the sun. But if you get to look at one of the new rapid scan images that GOES is taking of the weather, or you take a look at some of the hurricane or typhoon images on NOAA's Environmental Visualization Lab, you will see that amidst those swirling clouds, you can see lines. They all appear to be parallel, more or less, to one another, but they're all pointing back towards the center. The hurricane has the eye, the umbra. It has the swirling clouds in the atmosphere, like the sun does on the corona, but it also has these penumbral lines, these ridges. And these are different from the gravity waves, which can form ridges in clouds. These ones I'm talking about are much further apart, oftentimes dozens to up to 100 miles apart. But they are these ridges, and there is no meteorological explanation for where they come from or why they're there. Let's think a little bit beyond physical characteristics for a moment And let's think about energetic characteristics of sunspots versus Earth spots. And by the way, at this point, you should be figuring out Earth spots are the storms, the low pressure cells on Earth. Just like on the sun, the active areas are the sunspots. These are the stormy, energetic areas on the sun. Now on the sun, you have an active region or a sunspot group, and it is constantly flashing with low-level flares. We oftentimes call these nanoflares if they're small enough and numerous enough. And when they really let loose, when they really decide to fire, they produce a solar flare of extreme ultraviolet and X-ray energy that blows up the magnetic field lines, and it doesn't blow them up, it blows out up the magnetic field lines of the sun and out into space. Recap real quick. Sunspots, constantly flashing with low-level flares, but when they really let loose, massive electromagnetic energy into space, up the field line. On Earth, you get a low-pressure cell, and you have a bunch of storm clouds all together, just like you see a bunch of sunspots all together here. They're constantly flashing with low-level lightning, but when they really let loose, you get a sprite and a terrestrial gamma flash shooting up the magnetic field lines of Earth and releasing that electromagnetic energy into space. It's literally the exact same thing on a different energy level. There's no difference between them. Now, what I'm going to do here is I'm going to go ahead and get earth.nullschool.net up here. Thank you, Dex. Can we all see this here? This is known as the Earth wind map. And so basically you can, this thing's a little sensitive here. I'm hearing 1 second, we're having a mouse issue. Oh, this should help. Okay, so this is known as the Earth wind map, and you can basically take it, look anywhere you want around the Earth. You can zoom out, you can zoom in. And there's a bunch of other things you can do, like you can take a look at the pressure or the temperature. This is the temperature at the surface level. This is the temperature at the 250 HPA level, which is the jet stream. You can also look at things like relative humidity, the precipitable water in the atmosphere. But what I mentioned earlier, and the thing that's most important here, is the pressure. Let's just come over here right now. Okay, so what we have here is the wind overlay and the pressure overlay. The lines you see moving are actual direction of the wind. And purple is low pressure, yellow to white is high pressure. Now on this planet, all low pressure sucks in towards it. You can see it right up here and even more here. You see how everything's sucking in. All low pressure cells do that. On the north, they all suck in counterclockwise like this, and on the south, it's counterclockwise. Come to the high pressure cells, you can see this is all pushing out from the center. Not only is it pushing out from the center, but it's going the opposite direction, clockwise, of this low pressure cell sucking in. And on the southern hemisphere, that is flipped as well. Now, what's interesting is, first thing that comes to your head is, okay, well, here at this high pressure cell, and let me get rid of that earth thing there so it's a little easier to see. This high pressure cell, you clearly have air moving outward from my cursor. Where is it coming from? Here, you have wind and air moving inwards towards my cursor. Where's it going? Well, we know that the wind that gets sucked into the low pressure cell goes up. We know that the air is coming down from above here and spreading out. But would they spin like this if there was not electricity involved? If there wasn't magnetic fields doing this? What's more interesting is we see that these systems tend to change as the sunspots are changing. You might remember if you were watching this conference last year when Dr. Kong Papu Yen showed very, very convincingly how the sun and its activity will trigger tropical storm formation and intensification in addition to the earthquake triggers that we've been talking about today? Well, again, this is not exactly 100% perfect. However, when you see activity on the sun, one of these low-pressure cells, or maybe more than one low-pressure cell, will start getting really active. Or maybe a new one will pop up out of nowhere and immediately get a typhoon warning or a tropical storm warning. And what's even more interesting, when we see multiple sunspots firing all over the sun, we see tropical storms in the Pacific, the Atlantic, the Indian Ocean. When it's just one sunspot doing all the firing, there is a concentration of the tropical storms. We saw this a few weeks ago, maybe a few months ago, when there was 4 tropical storms around Australia at the same time. Just one sunspot going active at that time. Very active. So what we're thinking here in terms of Earth spots is that these are going to have magnetic fields that we can track, much like we do on the sun. On the sun, when you see those sunspots, they're actually magnetic fields, arches, that connect a positive sunspot to a negative sunspot. Well, if these are electrical, what's to say there's not an arc connecting that to that? From here to here. From here to here. Let me zoom in on the United States right now. There we go. We can take a look at this. So the United States, we have something that doesn't happen very often in the rest of the world. It does happen, but not as often. I am, of course, talking about earthquakes, and I wonder if this thing is going to come back anytime soon. I'm sorry, we're talking about tornadoes. Excuse me, I was flummoxed by the wind map not working here. There we go. Okay, so we're talking about tornadoes now. Where do you see tornadoes? Do you see tornadoes in the middle of the low-pressure cell? No. Do you see tornadoes in the middle of the high-pressure cell? No. You find them along what I've called convergence lines. You can see this area right here, or this area right here. What's happening is air, because it's a low-pressure system and it's all being sucked in, you have air coming from one direction on the planet, colliding with air coming in from another direction of the planet. And essentially what you have here is in this tiny little area, and this area of convergence is never more than a few miles wide. These two air masses must find an equilibrium in their temperature, their moisture, their electric potential, and their pressure. In chemistry, what happens when you have these changes physically? Back and forth, or chemically, back and forth. You have energy release. And it is along these lines that you see the severe storms pop up one after another. It is along these lines that you see the tornadoes. Let me zoom in a little bit more here. Now, what this is not able to do, and I guess it's not going to cooperate fully for me, along this little line here, there would be a bunch of tiny Earth spots. Very, very tiny Earth spots. We often see this on the sun where there's a massive sunspot and then a tail of tiny sunspots coming away from it. It must be hard to visualize if you're not used to seeing it, but if you watch the sun, think about it. You've seen this. One fairly large sunspot and then a tail of tinier ones curling away from it. That's what you're seeing here. And the energy is exactly the same. Now, what do we do in order to figure out where the Earth spots are? What do we do to start tracking this stuff? Because there are no satellites that are looking for this sort of thing. There's no ground-based monitoring of this sort of thing. We can detect, where magnetic fields are generally coming in and out, like the L shells of the planet and the magnetic field. But these are different. These are like the sunspots, truly, and so you can't create a general sweeping field image. You have to go more detailed. These things change by the hour. And so what we would have to do, literally, let's see if I can zoom out here and get this thing to work again. No? Okay. What we have is we're going to need to have whoever designed this wind map, they can take it one step further. And it doesn't actually have to be them. And by the way, is that you guys moving that, or is it doing it on its own? All right, that is him doing it. Freaking ghost in the machine there. The person who made this, or somebody with similar skills, all it would take would be to take this base layer right here and, excuse me, when we, I've got it upside down. When we come and we click the Earth here, maybe there's another overlay for Earthspots. And instead of seeing all this stuff on the ground here, maybe you still see the color so you can delineate what's a low pressure cell, what's a high pressure cell. But there will be an arc. Where's my mouse here? There it is. There will be an arc coming out and attaching to a high pressure cell. Or from this high pressure cell to this low, and then more all along for the little ones where the tornadoes are popping. It would literally be just one step further, and we can actually track these things. Now, why do we want to track these things, and why do we care? Well, despite the fact that when we see a lot of tropical storm activity, we don't see as much seismic activity. That is really only about timing. Because you see, when a typhoon is heading for the Philippines, either a day before landfall or a day after landfall, we often see a massive earthquake. We see this with Mexico as well. When the East Pacific hurricanes are rushing up towards Baja from closer to Central America, oftentimes, as it is rushing up there, either just out ahead of it or just behind it, you see an earthquake on that subduction zone that runs along the southwest coast of Mexico. Those two areas are the two areas where we see this more than anywhere else. I call those my Earthspot areas. Because anytime you see a tropical storm heading from the West Pacific towards the South China Sea, or you see an East Pacific hurricane or tropical storm cropping up, most of the time you can expect earthquakes in that exact place. Now, there are also single event Earthspot events, or basically, one time it happens and you don't really see it that often. Do you guys remember a couple weeks ago there were a bunch of 4-point earthquakes that struck in Michigan? That was the day, they started the day after those horrible storms came through. And they even dropped a tornado about 200 miles west of Detroit. We've seen this when the hurricanes that are in the East Pacific decide that, hey, we don't like it here. We're going to rush up to the desert of the U.S. This would be when you folks who are local here to Phoenix, when you guys got a year's worth of rainfall in 48 hours, happened about 4 or 5 times over the last 2 years. Did you guys notice there were an increase in small level earthquakes? You might not have noticed because there was no 5 magnitude earthquakes, no 7 magnitude earthquakes. This is Arizona. But if you watch down to the lower magnitudes, there was an increase from, basically the baseline up to magnitude 3. I don't think there were any above magnitude 3, but there were a lot more during those times when those hurricanes were actually coming up and dumping all that water on you. So what exactly is causing this? This is perhaps the most interesting thing, because the idea that an earth spot and a storm could affect seismicity is taking this jump to another level. Something that's a little bit out of the comfort zone, even if you are really well ingrained in this stuff. Unless you realize that it's not just that there's a storm there, but there's probably a magnetic field coming out of the earth at that point as well. And we have seen magnetic field and electric field fluctuations, electric current fluctuations before these seismic events. Well, what about forgetting energy? We're just going to look at what's happening physically, kinetically. What happens when a low pressure cell comes over an area, or a high pressure cell? We're talking about the downward pressure. This is amplified when we're over water because you're raising or lowering the sea level. Can you imagine what that does to the pressure on the ground below? So we literally, if we begin to think of earth spots like sunspots, we begin to come up with a lot of explanations for how how all of these things work. And when you think about pressure and how that would affect sea level and things like that, you realize that you have to start with the electric universe to recognize these Earth spots, and then you round it up with everything we already know. And you got to piece it all together, sort of like that. Anyway, I wish I had more stuff to show you. Like I said, it's just a very, very brief little introduction to Earth spots and what they are. There will be a lot more actually coming. There's a lot more on suspiciousobservers.org, and my book will be done in about a month and a half, 2 months, and yeah, I hit this topic pretty hard. But anyway, guys, thanks. Feel free to email me with any questions on this. My email is ben@observatoryproject.com. And I love talking about this stuff night and day. And I think that if I can get Kong Pop to get his hand on this, I might be able to just step back and watch a real genius do something good with it. But anyway, thanks for listening. That's my introduction to Earth spots.